think we're going to be working on this new chapter now we're starting, which is chapter 17, representation learning and generative learning. So yeah, let's see how far we can get. We'll catch up at about 50 minutes past.
That's fine. Yeah. Just one thing, I saw the message this morning from Joseph.
Yeah.
So he updated his schedule.
Let's have a look, because I thought I checked it earlier on today, but maybe he's changed it. Let me have a little look.
He added a day. I think now it's kind of like a 5 sessions we're gonna have for this.
Yeah. So he's done. Let's be able to show you. Yeah, he's made them extra for these couple of chapters, as I recall. So have a look.
Reinforcement learning is for 3 weeks.
Yeah.
And so it's like 6 sessions and a 5 lesson for this representation learning. So,
yeah. So yeah, we've got 5 for the representation learning, which is probably a good idea, because this is really quite complex and quite interesting as well. And then reinforcement learning, yeah, he's done 5. Actually, there's 6 sessions for that.
6 sessions, yeah.
Okay, good, great. We might be able to cover it like a couple of times with the. I don't always watch the ones on Wednesday night, I have to say, but like, yeah, that's great. Unfortunately, Parish's dad's not feeling well, so I'll probably do the reinforcement learning ones as well, unless you fancy doing them.
I never read them.
Yeah, don't worry, I'll do it. I mean, I don't know a lot about it, but I don't mind picking it up. It's an opportunity, it's an excuse to actually learn it, because otherwise I might not learn it.
Yeah.
Cool. So yeah, we'll catch up in about 45 minutes time, at 50 minutes past.
Okay, yeah, okay. So 50 past 6, we'll meet there.
Yes, okay.
Cool. Talk to you then.
Right, bye. Oh, hey, Dinesh.
Hey,
How you doing? Let me share my screen.
sure.
Can you see my screen? Yeah.
Yeah, I do.
Cool. Yeah. So chapter 17. Really interesting chapter, actually.
Yeah.
It's not something like I've studied before, but yeah, it's amazing stuff. Okay, so let's begin it.
Mhm.
So autoencoders are artificial neural networks capable of learning dense representations of the input data called latent representations or codings. So yeah, so essentially a dense representation is, I mean, it's the exact opposite of like a one-hot vector. So you know what a one-hot vector is, isn't it?
Yeah,
It's
yeah,
a, yeah, a vector all zeros except for one place where it's one.
yeah.
Well, dense is a vector which has got data in virtually every dimension. Um, and so another name is latent representations or codings. This is like in this particular situation. Okay.
Mhm.
So one of the things autoencoders are used for is what's called dimensionality reduction. I mean, you can imagine the input is, say, an image which is 28 by 28, which is 784 pixels. So 784 values, and maybe the internal dimension inside the autoencoder is only, say, 100. Well, that's kind of a sort of dimensionality reduction that's happened. Does that make sense?
Yeah.
Okay. So autoencoders also act as feature detectors, and they can be used for unsupervised pre-training of deep neural networks. So this is the quite interesting bit that I'm quite interested in. So
Mhm.
the idea is, I mean, let's say you've got a huge amount of unlabeled data, let's say text data, and but you've only got a limited amount of labeled data. It would be quite nice if you could create a neural network that somehow could detect a lot of the features in the unlabeled data, and then you could use those features with the limited amount of labeled data that you've got to create some kind of an interesting model with that. So yeah, so that's
So,
quite an interesting use.
I'm
Sorry.
like, yeah, so usual, like a normal deep learning neural net, it is capable of capturing all the features. What's the difference in here? I'm like, when we push any image, let's say our MNIST or a fashion MNIST, to a deep neural network, that's the neural network is doing. It's picking up a different features layer by layer.
Yes, it is. But that's fashion MNIST. You've got quite a large labeled data set.
Mm.
I don't know how many images there are in that data set, but there's, I think it's about 80,000, isn't it?
Mm.
What if, your labeled data set only had like 100 images in it? How would you be able to use a neural network to handle that situation? There's so little data to train a model on. You're quite right. If you had the data, if you had the labeled data, then you could just do an end-to-end model that would kind of do the job. But if you're in the situation where the amount of data that's actually labeled is like only a tiny amount,
Mm.
then you need something on top of that, so to help you out. And autoencoders are one possible approach that you could use.
Mm. Mm.
Because the idea is that the autoencoder is going to learn a whole load of features. I mean, let's say, we were talking about, let's say you only had 100 labeled images of houses, that you were detecting.
Mhm.
Because for some reason you're in like realty, and you're like an estate agent, and you want to be able to kind of classify houses. Well, if you could just on the internet get tens of thousands of house images, which are not labeled with what type of house they are, but you could somehow use this dimensionality reduction to sort of convert that image to, like, say, a 30-dimensional vector for each one of them. And then using the labeled bit, which you've only got a couple of hundred, train using that to kind of do the classification. You're still going to get a better model than just training it on that 100 labeled data that you had. So this is what the hypothesis is, that unsupervised autoencoders, so just using it on a whole load of data, because they've got this kind of compression element in that they detect the features, you can use that those unsupervised features to help you out with whatever model you were trying to build with the limited amount of label data that you had. Yeah.
Yeah. Okay. Yeah, makes sense.
Okay. So lastly, some autoencoders are generative models. They're capable of randomly generating new data that looks very similar to training data. So I think we're not going to get to generative models this week because they're a bit further in the chapter. But yeah, but these are really interesting. They're like the famous examples you see on the internet of images of people that don't exist, but they look remarkably like they should. So
Yeah. Did you see that? I think it's the next page. This person does not exist.
yeah, I didn't go to that website, but I follow a guy on the internet, and his name is Abhishek Thakur. He's like I don't know, you probably heard of him as well.
I know. I saw him on the he's on the LinkedIn as well as YouTube videos.
Yeah, so I'm not sure exactly how Abhishek Thakur. Yeah, this guy. I'm not connected to him, but yeah. And let's have a look at his posts. Where's his activity? And posts. And then, okay, that's something or other, that's something or other, that's something or other, and then something or other. Sorry, I'll just get there in a second. He posts a lot of stuff on LinkedIn. He's really very active on here. Oh, okay, he works for Hugging Face. So, okay.
Sorry, I just give me 1 second, okay?
Yeah, no worries. You go ahead and answer your phone.
Sorry about that.
No worries.
This is my plumber come handyman, which I was chasing him since December.
All right. Yeah, so he built this model to get this character to do the dance that he's actually doing. Yeah. So I'm not sure that's a real person. I wonder if that's generated as well. I didn't go into it fully, but there's no reason why you couldn't kind of combine a little bit of it. But yeah, it was still really, really cool because like it's lips and everything. So yeah, these generative models are like amazing.
That's correct.
So yeah, cool.
It could be like generated even if you go to that this person does not exist.
Yeah.
Which is you could end up spending a really good time there because like this how come I showed it to my family and it's not now, in the past I said, look, this person does not exist, and they said no, they nobody believed me.
Yeah, and then this is cool. I haven't been to this guy, but like
realistic.
I mean, these are just so amazing. They're just so detailed.
Yeah.
And this is a decent sized image as well. This is not like a 28 by 28.
Not at all.
Yeah. Sometimes apparently some of these have like slightly weird artifacts, but all these are like really fantastic. Although mind you, they're probably handpicked to be really good examples.
Yeah, maybe yeah. So maybe somebody has just stored them, not generating it.
Yeah, I'd be surprised if you generate on the fly.
Yeah,
because that was really quick. But yeah, they're amazing, aren't they? It's like the level of detail is like absolutely astounding.
Yeah.
Yeah, as I said, these things are just like so cool.
Absolutely, yes.
Okay, so carrying on with the boring book. So, in contrast, faces generated by generative adversarial networks are now so convincing that it is hard to believe that the people they represent do not exist. And they've also got this Airbnb rentals that do not exist as well.
Yeah.
And GANs are now widely used for super resolution, increasing the resolution of an image, colorization, powerful image editing, replacing photobombers with realistic backgrounds, turning a simple sketch into a photorealistic image, predicting the next frames in a video, augmenting a data set to train other models. I mean, this is something I'm quite interested in. And generating other types of data such as text, audio, and time series, identifying the weaknesses in other models and strengthening them and more. Yeah, I mean, it's so amazing. Right, so autoencoders. So autoencoders simply learn to copy their inputs to their outputs. That's because the input shape is the same as the output shape. So this may sound like a trivial task, but we will see that constraining the network in various ways can make it rather difficult. For example, you can limit the size of the latent representation. So this is the dense, kind of the dense layer in the middle. Or you can add noise to the inputs and train the network to recover the original inputs. These constraints prevent the autoencoder from trivially copying the inputs directly to the outputs, which forces it to learn efficient ways of representing the data. In short, the codings are byproducts of the autoencoder learning the identity functions under some constraints. Okay, so that's is that okay? So it's doing this, trying to copy the input to the output, but there's stuff in the middle that's making it more difficult. So it's having to learn how to do something clever rather than copy input to output. Yep. So GANs are composed of two neural networks: a generator that tries to generate data that looks similar to the training data, and a discriminator that tries to tell real data from fake data. This architecture is very original deep learning in that the generator and the discriminator compete against each other during training. The generator is often compared to a criminal trying to make realistic counterfeit money, while the discriminator is like the police investigator trying to tell real money from fake. Adversarial training competing neural networks, is widely considered as one of the most important ideas in recent years. In 2016, Jan LeCun even said that it was the most interesting idea in the last 10 years in machine learning. It's interesting he doesn't mention the name of the guy who did it. I think it's Ian something or other.
Goodfellow, yeah, Ian Goodfellow, yeah.
Yeah, Ian Goodfellow, yeah.
He's the one who discovered these GANs.
Yeah. I mean, once you think of the idea, it's obvious, but actually to come up with it, wow, it's really, really cool. So, yeah. And he said, we will start by building a simple generative adversarial network to generate fake images, but we will see the training is often quite difficult. We will discuss the main difficulties you will encounter with adversarial training, as well as some of the main techniques to work around these difficulties. So that's a little bit of a forward to the GANs, that actually training is quite tricky for them, but there's techniques. So let's start with the autoencoders. So, and here is a little puzzle saying which of these sequences is easier to remember. This sequence is short.
Yeah.
The other sequence is much larger, but there's actually a rule involved. And so for humans, at least, this second one is much easier to remember than that one. And the whole notion is that if there was some pattern in the data, then you should be able to, in some sense, reduce the size of the representation. For instance, this could be like just a very simple formula to regenerate for any input what for instance the next one is in the sequence. So this is kind of the idea of it. So, and it says the fact that it is hard to memorize long sentence sequences is what makes it useful to recognize patterns. And hopefully this clarifies why constraining an encoder during training pushes it to discover and exploit patterns in the data. So does that kind of sentence make sense?
Yeah.
Yep.
Now, obviously, when we are looking for, like, especially with the numbers and the sequences, you're not going to remember. All you're looking is the patterns, and even those puzzles comes in where you need to solve something. All you're looking is just any hidden pattern in it, whether it's even numbers or odd numbers, or is a gap of certain numbers, or it's scarce, or all that sort of stuff.
Yeah, I mean, even some of these guys who do amazing feats of memory, they learn like patterns. So I'm not sure exactly how they do it, but some of them, they kind of imagine walking from home to some place, and then each step of the way is one of the things they've remembered. So like they associate it in some way. So they don't remember the original kind of like all the numbers they need to remember. They remember like I know how to go walk from my home to my office, and if I identify a number with each place that I'm going, then I can remember the whole sequence just with the fact that I'm moving through from place A to place B. So yeah, but, I mean, there are some people who've got like amazing, sort of ability to remember things, but apparently they all use these kind of patterns, these kind of shortcuts to do it.
They do, and one of the, I think, those, I think it's a blackjack guys. You're not supposed to remember because it's a deck of 3 cards, but then I think there are few people who cracked it, who are able to kind of like remember or know the pattern, what the next card is going to come, if you know what I mean.
Yeah. I card counting, I think, isn't it? Is one of the names for it. Yeah.
And it's
I know it's illegal, but yeah.
It's illegal, but it's again sort of like a pattern. I was reading some, or maybe somebody's blog, and he said he don't remember everything. It's kind of like he has an eyes, and the patterns start coming up automatically.
Yeah. Interesting.
It's not even a remembering like what has gone, what is coming, but it's more of like what the next probability of a next number.
Yeah,
that comes automatically to them. I don't know how they do it, but that's another interesting.
Yeah, same here. I mean, they've got this little paragraph about chess players. So apparently the relationship between memory, perception, and pattern matching was famously studied by William Chase and Herbert Simon. They observed that expert chess players were able to memorize the positions of all the pieces in a game by looking at the board for just 5 seconds, a task that most people will find impossible. However, this was only the case when the pieces were placed in realistic positions from actual games, not from the pieces were placed randomly. Chess experts don't have a much better memory than you and I. They just see chess patterns more easily, thanks to their experience with the game. Yeah, so that's interesting. They've kind of gotten heuristics about what stage of the game is at, and because this is the way that they've because chess is not purely random. Although things can be in any place, a lot of games follow a certain trajectory until there's like somebody does something a little bit unusual, I guess. But yeah, that's interesting as well, that humans, we naturally, have got these kind of like shortcuts to trying to remember something quite complex by having something else which is a bit more abstract but simpler.
Yeah.
So just like chess players in this memory experiment, an autoencoder looks at the input, converts them to an efficient latent representation, and then spits out something that hopefully looks very close to the inputs. An autoencoder is always composed of 2 parts, an encoder or recognition network that converts the inputs to a latent representation, followed by a decoder or generative network that converts the internal representation to the outputs. So here they've got an example of one where the inputs are x1, x2, and x3, and then they go into something where the encoder is actually only 2-dimensional now, so these 3 inputs somehow have to be encoded into these 2, and then the output is back into 3. So this is kind of an auto-encoder, a kind of diagram of one. The encoder and the latent representation is here. So these are the inputs, and these are finally the outputs, and this is the decoder bit of it. So I guess that diagram makes sense. Yeah.
Yeah. So the one question I would have is like, how would we have been like, this is unlabeled thing. So how it's making sure, because we don't have a label data. On a label data, we compare the output and we say, oh yeah, he did a good job. But now we don't have the label. How we make sure the outputs are the outputs which we are looking, is the outputs are equivalent to the inputs.
Right. So this is really where the real cleverness of it. It's really simple, but during training, you always give the input and the output as the same. And that's what forces the network to learn what the latent representation should be. So you're all, but this is during training. Obviously, during evaluation, you're just giving it an input and it's kind of doing something to it to convert to output. Maybe it's denoising it, or maybe it's colorizing it, or whatever it's doing to it. But the idea is that during training, you give it obviously what you expect to get back. Yeah, in some sense, that is kind of labeling it, but you're sort of, in the simplest case, let's say that you were doing this to text. Yeah, well, you'd give the same sentence as input as the sentence as output. And then the encoder decoder, the bit in the middle, would have to somehow compress the original input sentence to make sure that it could generate the output sentence to be exactly the same. Does that kind of make sense?
Kind of, yes. Yeah.
Yeah, so this is where I mean, usually, you know, our inputs are not the same as the outputs. I mean, why would they be? But in autoencoder land, they are the same as the inputs are the same as outputs. And this is why we, you know, when we've got like a huge amount of unlabeled data, why we might want to use an autoencoder to kind of learn this latent representation. And then we chop the decoder bit off and then add on top whatever classification or whatever we want, because the encoders learned a whole load of features now, which could be useful for our purposes, in that our new model is not having to work on the original full text. It's working on this kind of, you know, compressed latent representation, you know, and this is why it's really useful for a lot of cases where you've got a huge amount of unlabeled data and only a little bit of labeled data. Yeah.
Okay. Yeah. All right.
Okay, so it says, as you can see, an autoencoder typically has the same architecture as a multi-layer perceptron, except that the number of neurons in the output layer must be equal to the number in the input. Yeah, because the idea is that it's trying to copy the input to the output. Yeah. Okay, so the outputs are often called the reconstructions because the autoencoder tries to reconstruct the inputs. And the cost function contains a reconstruction loss that penalizes the model when the reconstructions are different from the inputs. Yeah, so this is how we train it. We give you the same input and the same output, and the loss function is what it's kind of measures the difference between the actual output and what you were expecting the output to be, which is the same as the input. Okay. And it says, because the internal representation has a lower dimensionality than the input data, so in this case, the input data was 3-dimensional and the internal representation was 2-dimensional, the autoencoder is said to be undercomplete. So this is where the middle bit is actually got lower dimensions than the input. That's called undercomplete. And under a complete autoencoder cannot trivially copy its inputs to the outputs. Yet it must find a way to output a copy of its inputs. It is forced to learn the most important features in the input data and drop the unimportant ones. Yeah, so you can't just copy the input output because there's not enough, and there's not enough dimensions in here. It has to somehow kind of detect what features are needed to be able to generate the correct output. So let's have a little look at how they use it. So if the autoencoder uses only linear activation functions and the cost function is the mean squared error, then it ends up performing principal component analysis. Oh, that's interesting. So yeah, it is equivalent to that. So the following code builds a simple linear autoencoder to perform principal component analysis on a 3D data set projecting into 2D. Yeah, so here, this is their 3D data set. And then they're projecting it to 2D. So you can see it's kind of kept most of its shape so they could reconstruct the 3D. So it'll be interesting how it encodes the Y dimension. I guess there must be some element of that somehow encoded in there. But let's have a little look. All right, so this is the bit of code. So it's a sequential. There's a dense layer. So the input is 3-dimensional, the dense layer, the output is 2-dimensional, that's the encoder, and then the decoder takes the 2 dimensions and converts them back to 3 dimensions. And the whole encoder decoder is an encoder followed by a decoder as a sequential kind of model. And the loss is the mean squared error. Does that little bit of code make sense, what it's doing there? Yeah. Cool. So this is just an explanation of this code. So we organize the autoencoder into 2 subcomponents, the encoder and the decoder. Both are regular sequential models with a single dense layer each, and the autoencoder is a sequential model containing the encoder followed by the decoder. Remember that a model can be used as a layer in another model. Okay, so this is a KRS thing. The autoencoder's number of outputs is equal to the number of inputs, which is 3. To perform simple principal component analysis, we do not use any activation function, i.e. all neurons are linear, and the cost function is the mean squared error, We will use more complex autoencoders shortly. Okay, so this is specific to do with principal component analysis. You just use normal matrix multiplications. There's no non-linearity added anywhere. Yeah. So note that the same data set, XTrain, is used as both the inputs and the targets. Shows the original 3D data set on the left, and the output of the hidden autoencoder layer, because it's two-dimensional, over here. As you can see, the autoencoder found the best 2D plane to project the data onto, preserving as much variance in the data as it could, just like principal component analysis. Yeah. You can think of autoencoders as a form of self-supervised learning, i.e. using a supervised learning technique with the automatically generated labels, in this case simply equal to the inputs. Yeah. So inputs, outputs the same. And you can think of that as kind of self-supervised is kind of a name for it. Is that all kind of okay?
Yeah, so all we are saying is when we pushing input into 3 input into next hidden layer with only 2 neurons, it's gonna squash the data, like it's gonna squeeze, or like going to learn or having a representation. So that's kind of like, because we reduced 1 dimension, that's a PCA automatically.
Yes. Okay. Yeah, so you reduce from 3 dimensions to 2 dimensions. Yeah. And then we've got stacked autoencoders. Okay, so just like other neural networks we have discussed, autoencoders can have multiple hidden layers. In this case, they're called stacked autoencoders or deep autoencoders. So here, for instance, we have got an input layer, then we got 1 hidden layer, then we got another hidden layer, and then we can regard this as the encoder, and then we got another hidden layer, and then the output layer, and that's kind of the decoder. But the idea is that you can have a lot more structure in the middle, not just one single kind of layer, a bit like we had just as an example before. Yeah, you can make it as deep as you need to make it for whatever you're trying to do with it. Is that kind of okay?
Yeah, that's fine.
Yeah, but they do give a little warning that said one must be careful not to make the autoencoder too powerful. Imagine an encoder so powerful that it just learns to map each input to a single arbitrary number, and the decoder learns the reverse mapping. Yeah, so that's kind of like going a bit too far in that there's so many weights in there that it learns to, the encoder maps it to one single number, and then the decoder takes that one number and converts the output again. Obviously an extreme case, but yeah, you got to be a little bit careful in not making them too powerful. Otherwise this latent representation is not sufficiently interesting, because all the interesting stuff is happening in here because it's got too many weights in these other layers. Okay, so that's interesting.
Yeah, so this is just it's just a linear learning, the just simple deep learning. So there is no activation, there is no loss function, or there is a loss function.
Loss function is mean square error, because the inputs are like compared to the outputs. Although they do use a couple of other loss functions later on. There's like a cross entropy as well.
And there is a and there is a back propagation is going as well.
Yes. It's just a normal, like a deep neural network.
Yeah.
Except with just linear layers. Yeah.
That's fine. So, but there is no so there is no activation going then.
Not in these guys, no.
What I'm trying to get into is like the whole point of the the back propagation which we do, or the stochastic gradient descent. We want to have a learning but don't remember the data itself, and that's the whole point of deep learning, and that's exactly what he is talking. That you need to be very careful.
Yes.
However, in I think in case of deep learning, we have this L1 and L2 regularization, or a dropout as well. We have different techniques where we prevent the model to learn the data, remember the data. So what do we? So do we do something similar or same thing in here as well, or do we have a different techniques to stop it, making it a very strong?
so that you can just remember it rather than learning a pattern?
Yeah, they use the same sort of approaches, dropped out, regularization, because essentially what you're trying to convince it to do is to learn something really interesting in this hidden layer. This the decoder, this latent representation. You're trying to make it to learn as many features as it can and not try and just remember the data. And so, yeah, exactly the same, approach is regularization, dropout, and they're going to come to that later in the chapter, how, and even the activation functions. I mean, here, cell U is already being added now. But there's no reason why you can't have activation functions, but they're saying basically, if you want to do what's called just principal component analysis, then not having any nonlinear functions here will do that for you. Basically, that's essentially what the network is doing when you don't have any nonlinear functions in here. It is doing principal component analysis. But if you add in nonlinear rarities and dropout and regularization, then it's going to do something different. That's not principal component analysis. It's going to learn something a little bit more different.
Second, what was the last? It's not a PCA in what case?
If you add in nonlinear rarities, like nonlinear activation functions, dropout, and regularization, then all those things mean that it's not doing principal component analysis. It's doing something different.
Why do you say that? Because if let's say I just introduce I still have the hidden layer for 100 unit and 30 units, which is like reducing the layers or the nodes so that there is no one-to-one mapping. So what difference it's going to make then?
No, well, you have to remember a little bit about, this is about what is principal component analysis. So principal component analysis is kind of essentially a convoluted way of rotating and then projecting the data. Yeah. So what principal component analysis does is it finds a rotation which aligns the best with the number. Like, let's say you're going from 5 dimensions to 3 dimensions, yeah? So what principal component analysis does is it kind of rotates all the data so that it lies in the best 3-dimensional plane you can find, and then projects all the data onto those 3 dimensions. Yeah. And that doesn't require any weird nonlinear stuff. That's just rotations and then projections. Once you start adding these nonlinear operations, things like ReLU and CellU and sigmoid, that's not principal component analysis. This is going to do something else to the data. This is not just rotation and projection anymore.
So there will be so you mean in a PCA you have just the linear transformation?
Yeah.
But if you introduce a non-linear transformation to a data, it's not a simple projection or a simple linear transformation. It's like a complex projection.
Yeah.
Okay.
Yeah.
All right. Okay.
So here they're implementing a stacked autoencoder. So with a little bit more structure in the middle. And they're saying normally with stacked autoencoders, they're symmetrical about the middle. So whatever is the structure from the input layer to the hidden, you kind of reverse it around, mirror it, and do the opposite on the way out. I mean, you don't have to do that, but for stacked in autoencoders, that's usually the architecture that you use. Yep, is that kind of okay?
Yeah, that's fine.
Okay, so this is so this was an implementation of this kind of example for MNIST, the 28 by 28. So here they are saying that they use a slightly different loss function for stacked autoencoders. So when compiling the stacked autoencoder, we use the binary cross entropy loss instead of mean squared error. We're treating the reconstruction task as a multi-label binary classification problem. Each pixel intensity represents the probability that the pixel should be black. Framing it in this way rather than as a regression problem, which is what you would do with mean square error, tends to make the model converge faster. So this, I mean, either loss is okay because they're just numbers, but this binary cross entropy seems to make the model converge faster, which I thought was an interesting kind of aside if you're ever implementing it. Yeah. So here they're looking at visualizing the reconstruction so that, when you're given a certain input, what does the output of the autoencoder look like? So this is an example of it. So these are the inputs at the original at the top and what the autoencoder is outputting. So you can see it's a little bit fuzzy, and you know, I mean, you can recognize that, you know, what is what really. You can know that's a shoe and that's like a t-shirt, but the output is a little bit fuzzy. It's never going to be perfect because, you know, obviously this latent representation is not perfect. But it's interesting. So it says the reconstructions are recognizable, but a bit too lossy. We may need to train the model for longer, or make the encoder and decoder deeper, or make the encodings larger. But if we make the network too powerful, it will manage to make perfect reconstructions without having learned any useful patterns in the data. So yeah, I mean, I know the inputs and the outputs are not looking fantastic in terms of just comparing input out, but actually there's interesting information here which might be interesting to you in a completely different type of model. I mean, for instance, if you were creating a model that was classifying things as shirts, you know, shoes, that potentially what this model has learned could actually be of interest to you in classifying those. Do you kind of understand what I'm saying?
Yeah.
Okay, so visualizing the fashion evidence. Now that we've trained a stacked autoencoder, we can use it to reduce the data set's dimensionality. For visualization, this does not give great results. So we've seen that here. To other dimensional reductionality algorithms, such as those we discussed in Chapter 8. But one big advantage of autoencoders is they can handle large data sets with many instances and many features. So one strategy is to use an autoencoder to reduce the dimensionality down to a reasonable level, and then use another dimensionality reduction algorithm for visualization. Let's use this strategy to visualize fashion MNIST. First, we use the encoder from our stacked autoencoder to reduce the dimensioning down to 30. So the original was 784 because these are 28 by 28 pixels, but we reduced it down to 30 now. Then we use the scikit-learn's implementation of TSNE algorithm to reduce the dimensionality down to 2 for visualization. So here, yeah, so this is TSNE is usually what we use to visualize something that's very high dimensional down into 2D. And so what this image is showing is that actually different regions are the different types of things that were in the MNIST images. And so this is quite, you know, good. You know, so the network has kind of recognized interesting features in the 30 dimensions, even though obviously this is only 2-dimensional. Does that make any sense?
Yeah, it's TSNE is more like cluster, same things around. Yeah.
Yeah, because it's only 2-dimensional, and it was 30 dimensions converted to 2 dimensions, it loses a lot of information. But it's interesting that even in 2 dimensions, kind of like handbags all lie in this segment, and shoes all lie kind of over here. And yeah, trousers lie over there.
Would you know what's the difference between TSNE and PCA?
I'm not sure, actually. Yeah, I'd have to look it up. But I mean, it's doing the same sort of thing. Projecting something from a higher dimension down to 2 dimensions. I just wonder if there's something, you know, special about 2 dimensions that they've done. That maybe it's kind of yeah, making it that it's within a certain region, or, you know, it knows what the boundaries of the region are, or something like that. But yeah, I might have to find out. It's a good question, actually, you've asked. There might be a YouTube video about it as to what the difference is.
Yeah. Well, one thing I think I remember somewhere the conversation, it gives you clusters. Like if you look at this this picture, so this picture has given you the cluster of where each element lie, and I think the PCA is more of the projection of the points. So it's
it'd be interesting.
Confined information, something like that.
Yeah,
I don't know.
Yeah, could be.
As you
could
said,
be.
we need to look into it into detail.
Yeah, it sort of makes sense. I mean, yeah, normally the TSNE, that's what you see is the clusters. So it is very interesting. Yeah. So we got on to the unsupervised pre-training using stacked encoders. As discussed in Chapter 11, if you're tackling a complex supervised task, but you do not have a lot of labeled training data, one solution is to find a neural network that performs a similar task and reuse its lower layers. This makes it possible to train a high-performance model using little training data, because your neural network won't have to learn all the low-level features. It will just reuse the features detectors learned by the existing network. Similarly, if you have a large data set, but most of it is unlabeled, you can first train a stacked autoencoder using all the data, then reuse the lower layers to create a neural network for your actual task and train it using the labeled data. So for example, in figure 17.6, so for instance, this was, so we had a huge amount of unlabeled data. We used this stacked model to train on that. And then we only use this bottom bit of the autoencoder in our new model. So we use these three, but then we added in a little bit of extra structure, like there's a dense layer and then a softmax to on our labeled bit of data to use it in our algorithm. So the idea is that all the stuff that this network learned is going to be useful for this guy, but we only have a limited amount of labeled data now to train this guy. But we're hoping that the performance is going to be quite good because of all the features that this guy has learned. So this was what I was talking about earlier on. Does that make sense?
Yeah. Okay. So it's interesting. It's like the other way around. I thought first you train on a labeled data, and then you go to the unlabeled data to tell that, okay, I have given you a kickstart on like 100 labels, but now make your mind afterwards on the huge volume of data to train. But here you're saying it's just the other way around, that we train the autoencoder initially without a label data, and once it has trained, then we pass it on to the label data, which is less number, and then fine tune it.
Yes, yes.
Okay.
Interestingly, they actually trained this guy with all the data. So it says train the autoencoder with all the data. So all the labeled data and all the unlabeled data, because I mean, basically the labeled data you're treating is unlabeled. Yeah, and the reason you're wanting to do that is to make sure that even the data that's labeled, it still gets kind of, you know, this hidden state kind of learns its features as well. Yeah. And then you use that button bit. And then this second bit, which is the fine tuning bit, you only use the label data for fine tuning that.
Data to fine tune it. Okay. Yeah. Okay. Makes sense. Yeah. This is very interesting chapter.
Yeah. So he says, when training the classifier, if you really don't have much label trained data, you want to freeze the pre-trained layers, at least the lower one. So the idea is that you don't want to start undoing, you know, getting it to forget this. If you are having problems, you can freeze this little bit and only train the bits at the top there, if you know, to make. But that all depends on how much data you have and whether you're having problems with the network forgetting, you know, what it had learned here. So you've got a choice. You can freeze these layers and only train the bit at the top, or you can train it end to end when you're fine tuning. Yeah. Is that okay?
Yeah.
Okay. And then it says here, so having plenty of unlabeled data and little labeled data is common. Building a large unlabeled data set is often cheap. For example, a simple script can download millions of images of the internet. But labeling those images, for example, classifying them as cute or not, can usually be done reliably only by humans. Labeling instances is time-consuming and costly, so it's normal to have only a few thousand human labeled instances. Yeah, I mean, this is the problem 99% of the time. So yeah, so this whole approach is really, really interesting. And I think we'll just do this section, which is tying weights, and then we'll stop, because hopefully the guys, I mean, there's so much in this. I think the guys are going to be not going to get like a huge amount far, but we'll see how far they get.
Yeah.
So tying weights. When an autoencoder is neatly symmetric like the one we just built, a common technique is to tie the weights of the decoder layers to the weights of the encoder layers. This halves the number of weights in the model, speeding up training and limiting the risk of overfitting. Yeah, so basically what they're saying is, because this model is completely symmetrical, if we could, then essentially the weights that you've got here, you can actually reuse them here, because you can use the same weight here as here, and then you can use the same weight from here to here. Obviously, there's like a little bit of reshaping involved to make sure you know that you're using the weights in the correct way, but it virtually halves the amount of weights that you need in the model. Does that kind of make sense?
Interesting. Yeah.
Yeah, I mean, I was surprised you could do it, because but I can understand sort of that if this divides a value by 2, you want to multiply the value by 2. So like, I was like, okay, you know, but the weights can't be exactly identical, but I can imagine one is the opposite of the other. But actually they've got this thing called a transpose, which seems to do the right thing.
My only problem is the weights are going to be learned, you know. So
Yeah.
we are saying is that you train the encoder. And once you've done the training the encoder, and then you just copy over the weights to the decoder.
Yeah, so apparently they do it with this special layer. It's called a dense transpose layer. And this is what allows it to learn that shared weight that they've got. So yeah, I mean, I don't quite understand how this works, but apparently this is the way you share weights, is using this dense transpose layer. And it says this custom layer acts like a regular dense layer, but it uses another dense layer's weights transposed, such as transposed is equivalent to transposing the second argument, but it's more efficient as it performs the transposition on the fly within the matrix multiplication operator. However, it uses its own bias vector. Yeah, so it's not an exact kind of like, you know, you're not using exactly the same data in this hidden layer as this hidden layer. But I mean, like, you're using the same weights, but the biases are different. So it's not exactly identical, but it is kind of halving some of the weights in that the. But yeah, this is a non-trivial operation, so it's interesting that it even works. Yeah, I haven't fully got my head around how this works.
Yeah. Okay.
And then we've got. So with that, those shared weights and everything, says this model achieves a very slightly lower reconstruction than the previous model, with almost half the number of parameters. So yeah, it seems to all work. I'd have to get my head around it as to how this sharing works.
Exactly. Yeah. It makes a half a sense at this stage, because I think this is entirely a very different concept. Comparatively, we have been doing the deep learning, you know, the back propagation, and then you go step by step. But here it is a deep learning, but slightly different way they're trying to do, because we don't have a label, so it's just learning and then competing with each other, encoder, decoder. And
yeah.
need to look into a few videos, I guess.
Yeah. Okay, we'll just do one more section, this training one autoencoder at a time. Okay, so basically this is a little bit historical. So because we don't really do this now, but in the old days, when GPUs and, you know, compute was, you know, not as much available, they had this slightly clever technique, and it might be worth knowing about it. So it says, rather than training the whole stacked autoencoder in one go like we just did, it is possible to train one shallow autoencoder at a time, then stack all of them into a single stacked autoencoder, hence the name, as shown. This technique is not used as much these days, but you may still run into papers that talk about greedy layer-wise training, so it's good to know what it means. Okay, so what they're doing here is, so we remember that we had this this autoencoder, which had input hidden, and then this hidden, and then output. Okay, so what they're going to do is they're going to first train one autoencoder that's got an input and an output, and then a hidden layer. And they're going to train that end to end. And then what they're going to do is take the inputs and then apply this hidden state to give you basically what the output should be. And basically what you do at each point is you introduce, you kind of, you take the output of the network to train a slightly different autoencoder. So the idea is now what they're going to do is so let's have a look. Yeah, so what in the next, so that was the first autoencoder. The second step is where they kind of introduce this bit in the middle with the hidden bit in here as well. And so let's have a look how they do it. So during the first phase of training, the first autoencoder learn to reconstruct the inputs. So this is what they're doing. Then we encode the whole training set using the first autoencoder. And this gives us a new compressed training set. So so this is where the output of this guy, the compressed bit, is coming in. This is the second phase of training. Finally, so this is the second phase of training. So somehow they're training something which is on the output of that, So I guess so far you've got, so when you finish with this, you've gotten this whole bit already done, as it were. So the data is already in the right format to feed it into this bit. And then you're only training, and then you're copying the parameters of that one into that one, and then only training these two. Yeah, it's all, yeah. So yeah, I can kind of see what they're doing. So basically the idea was train this one first. You use all the data to generate what the output would have been here. And then you're sort of assuming that this had already been done in this version of it. And then you only train that bit of it because you're using the weights from that one, and you're using the weights from this one, and you're using the weights from this one. Does that kind of make sense?
No.
Yeah.
Perfect.
Yeah, so yeah, what they're saying is, so phase one is train this guy on all the unlabeled data.
Yeah.
And then what you do is for each unlabeled data, you feed it through this guy, but then take the output here. Yeah. So that's almost like these first two layers have done their job, and the whole data set is now reduced. Yeah. Let's say the output of this was only, so let's say the input was 100 dimensional, and the output of this guy was only 30 dimensional.
Yeah.
So now your whole input, your whole data that you started with is now all 30 dimensional, isn't it? Because you've applied just these two once they've been trained. And then what you do is you take that 30 dimensional data and you train these two guys with it.
The hidden 2 and hidden 3.
Yeah, the hidden and the hidden 3. And then you kind of put them all together when you finally, once you've trained those two, you fit them all together. And that gives you, and I said that I think the whole thing was, so there's a discussion about why this was done. I discussed earlier, one of the triggers of the current tsunami of interest in deep learning was the discovery in 2006 by Jeffrey Hinton that deep neural networks can be pre-trained in an unsupervised fashion using this greedy layer-wise approach. Yeah, so at that point, maybe the graphics cards weren't sophisticated enough to do really deep networks in one go. And so it was Jeff Hinton who discovered that you could do this, that you could train like small bits of the network, and then use that pre-training to train a little bit more of the network, and then finally you can put it all together to make the full deep network. And then it says, for several years, this was the only efficient way to train deep nets until many of the techniques introduced in Chapter 11 made it possible to just train a deep net in one shot. So this was all back propagation, I guess, and skip connections and all that kind of stuff. I can't remember exactly what was in Chapter 11, but yeah, I reckon they're just talking about full end-to-end back propagation is what they're talking about there. So I think we might stop there because I have a feeling the guys are not going to cover. If I find out tomorrow morning that they've covered more, maybe we can listen onto their video on Sunday before they start.
Absolutely.
Yeah.
That's
cool.
fine.
All right. Have a nice evening then.
Fantastic. Thanks so much. Thanks, Arshad.
Okay. All right. Bye.